Hello guys, I am Daniel Okanyo, a graduate student here at the Celestian University of Technology. I am a graduate student pursuing mathematics, and I would love to take you through the interesting world of cryptography. And the first thing that we are going to look at is finding GCD of two numbers using the Euclidean algorithm. So I have a sheet of paper over here that I'll be making references. So in case you see me looking over here, then it's what I've written on this paper. I don't want to miss anything. Now, in finding GCD, we have many ways of doing that, but the best way is to use the Euclidean algorithm. Sometimes it's easy to find a GCD. For instance, when you are being given let's say find a GCD of 2 and 4. Clearly you can tell from this that the GCD of 2 and 4 is 2. I find the GCD of 3 and 9. In this case you can see that the GCD of 3 and 9 is 3. But what if the numbers are very huge? What do we do then? Okay, so now we have to note that every pair, which is m and n, if this pair is not equal to 0, 0, then their GCD does exist. So if we have a pair m and n, and the pair is not 0, 0, because the GCD of 0 and 0 is 0, which is nothing. So if we have a pair m and n, and that pair is not 0, 0, then it means that their GCD exists. So we have to note that the GCD of m and n is also the same as the GCD of n and m. So for instance, if we have this is the same as writing the GCD of 4 and 2. Also, GCD of m n is also equal to the GCD of minus m of minus m n, and it's also equal to the GCD. Sorry, I made a mistake over here. The GCD of minus m n, and this is GCD of m minus n, and this is equal to the GCD of minus m and minus n. So if we have, say, GCD of 3 and 8, it will be the same as finding the GCD of minus 3 and 8, or GCD of 3 and minus 8, or the GCD of minus 3 and minus 8. So these equations are the same. Now you have to note, if you are being given, let's say, the GCD of, say, m and 0, now the GCD of m and 0 is equal to m, and the GCD of 0 and n will always be equal to n. So if you have the GCD of 2 and 0, it is always equal to 2. Any number over here will be here. So any number that is over here will be here. And if you have the GCD of, say, 0 and 11, then the GCD of this will be 11. I hope this is clear. So with this, we also have some rules of the Euclidean algorithm. And the first thing that you have to notice, if we have GCD of m and n, this is equal to the GCD of n and the remainder. GCD of m and n is equal to the GCD of n and the remainder. So an example is if you are being asked to find the GCD of 735 and 85. Over here you see, because of how the numbers look like, the numbers are very huge. So telling from this that's the GCD so it's kind of difficult. So the best way to do this is to use the Euclidean algorithm. And using the Euclidean algorithm, you can use this approach, or afterwards I'll show you how to use the second approach. So if you want to use this using the remainder formula, we can see that 735 is equal to, over here, 85 times 5 plus the remainder. So in this case, it's 735. This is the quotient, which is 85. So 85 times 5 plus a certain remainder. So meaning that the GCD of 735 and 85 is the same as the GCD of n. And now n is the second part, which is 85, and now the remainder is 55. So you see, now we have this. We have the GCD of 85 and 55. And you can go through the process again. Now this is the same as when you have 85. 85 has a quotient of this, 55, multiplying 1 plus a remainder of 30. So the GCD of 85 and 55 is the same as the GCD of 55 and 30. Okay, now the next step is you can also keep on reducing this. So if you keep on reducing this over here, 55 is the same as, it has a quotient of 30 and 1. We always use this as a quotient. Plus, now, what will be the remainder? The remainder in this case is 25. So the GCD of 55 and 30 so GCD of 55 and 30 can also be written as the GCD of 30 and 25. Now, if you get this, you keep on reducing till you get a 0 in the bracket. So when you have 30 is equal to, now this is our quotient, 25, multiplying 1 because 25 will go into 30 just once, plus a remainder of 5. Now we are going to see that the GCD of 30 and 25 is equal to the GCD of 25 and 5. So we have GCD of 25 and 5. And over here, you can straightforwardly tell that the GCD is 5. Now, if you want to keep on solving, you can also see that 25 is equal to the quotient 5, and it goes into 25 5 times plus a remainder of 0. So now GCD of 25 and 5 is equal to GCD of 5 and 0. And as I said earlier on, the GCD of any number and a 0 is that number. So over here, the GCD of 5 and 0 is 5. So meaning that if we have GCD of 7, 35 and 85, this is equal to the GCD of 5 and 0, and this is equal to 5. There is another way of solving this whole thing. When we, for instance, let's solve the same thing using a different approach. It's similar though, but let's see how it goes. Over here, we can write it this way. This is the bigger number. So we have 735, and this is equal to, this will be the quotient, 85. So 85 will go into 735 how many times? So in this case, we can see that it goes into it 8 times with a remainder of 30. Then we write the coefficient, we write over here the quotient first, which is 85. So 85 will be equal to, then we write the remainder, so 30, how many times will it go into 85? You can see that it is 2. plus a remainder of 25. Now after getting this, write the quotient again. So 30 and the remainder 25. How many times will it go into 30? Which is 1 plus a remainder of 5. Now the quotient again, the remainder, how many times? 5 plus 0. So the last non-zero digit of this is 5. So in this case, the GCD of 735 and 85 is equal to 5. So this is a way of finding the GCD of any two numbers using the Euclidean algorithm. Okay, so let's try one other thing. So another example is, if you have been given this, find the GCD of 167 and 43. You also have to note that if you have this, if the GCD of m and n is equal to 1, then we say that m and n are co-prime. So whenever you find the GCD of m and n, or any two values, and their answer is 1, then it means that the two numbers are co-prime to each other. So in this case, let's see. If we have 167 and 43, so we have 167 is equal to 43. So 43 times 3 plus 38. Now the same process again. We write the quotients first, 43, and this is equal to the remainder. How many times will it go into 43? Which is once. So plus a remainder of 5. We write the quotient again, 38. The remainder, how many times? 7 plus a remainder of 3. Then we write the quotient again, which is 5. Then how many times? So the remainder, 1 plus 2. Then we continue. So 3 is equal to 2, 1 plus 1. So 2 will be equal to 1 times 2 plus 0. So after getting this, the last non-zero number over here is 1. So meaning that GCD of 167 and 43 is equal to 1. Meaning that 167 and 43 are co-prime. So basically, this is how to find the GCD of two numbers using the Euclidean algorithm. If there is anything that you do not understand, kindly comment and I'll give you a response. So yeah, see you in the next video. Bye.